We have studied by now many pairs of operations that are inverse to each other. So we started long time ago with addition and subtraction being inverse to each other, doing and undoing things, multiplication and division. We recently went on to exponentials being inverse to logarithms. And we can write this for a bigger than 0, we have a domain a not 1, b bigger than 0. That's a domain when the exponential and logarithmic are equivalent to each other. So these are inverse operations. Now, the next question is, what's the inverse operation of differentiation? If I know that dy by dx is, for example, 2x, the question is, what is y? In this example, we can just guess that y is x squared. We know that the derivative of x squared equals to x. But is it the only function? No, it turns out that if you consider, for example, y equals x squared plus 1, its derivative is 2x as well. Or you can consider y equals x squared plus 2, or y equals x squared minus 1, and so on. So any function y equals x squared plus c, where c is a real number, gives us as a derivative 2x. So we call the operation of finding the function when the derivative is given, we call it integration. And we write this as integral of 2x dx equals x squared plus c. Okay, that's a bit of a complicated formula, and there are two things coming together, this sign of the integral and dx, yes, telling me what is a variable that I integrate by. It's the same, and c is the same as a notation for dy, for the derivative dy by dx. Whereas for the derivative we have two notations. We can write dy by dx equals to x, or we can write the derivative of y dash equals to x. For integral we have a single notation. So it's integral to x with respect to x is x squared plus c. Or shortly, integral to x dx is x squared plus c. Now, same as we did with differentiation, and I repeat, integration is the operation inverse to differentiation. So same as with differentiation, I need some rules, some generalizations. And remember that the first rule for differentiation that we learn is a derivative of x to the power of n was n, x to the power of n minus 1. Therefore, we'll learn first how to integrate polynomials, and integral x to the power of n dx is going to be, in order to get as a derivative x to the power of n, I need to differentiate x to the power of n plus 1. But the derivative gives me n plus 1 x to the power of n, so I need to divide by n plus 1. Yeah, so that's how I differentiate polynomials, integrate polynomials. For example, integral x cubed dx is x to the power of 4 over 4 plus c. Integral x to the power of minus 3 dx is x to the power of minus 3 plus 1 over minus 3 plus 1, which is minus 1 over 2x squared plus c, and so on. I can use this formula only if n is not minus 1. When n is minus 1, I would get here the denominator 0, and it's not possible to use it. What happens when n equals minus 1? We'll learn a bit later. When n is minus 1, this becomes integral 1 over x dx. And you remember that it was logarithm. So this is logarithm x plus c, but we will see this in more detail later. So until we get used with the operator of integration, we are going to use just this formula. I write it again. Integral x to the power of n dx is x to the power of n plus 1 over n plus 1 plus c, with c being any real number and n being any real number, n is not minus 1. Okay. Now, what happens when I integrate the sum of two functions? Like I have, for example, I can have integral x cubed plus x to the power of 4 dx. Sometimes here we can put brackets, other times no, it's not necessary to put brackets because we know that integral starts at the integral sign and ends at dx. So I can write this. Remember that we had a rule for the derivative. When you differentiate a sum is the same as differentiated each of the functions separately. Now if we think that integration is the undoing of differentiation and go from here there, then we'll see that integral of x cubed plus x to the power of 4 is the same as integral x cubed dx plus integral x to the power of 4 dx. Of course, with time we'll not write in such a detail. So this is going to be x to the power of 4 over 4 plus x to the power of 5 over 5 plus c. We get a constant, actually, we get a constant from this integral, so it's plus c1, and the constant from this integral plus c2. But when we add two constants, they make a single constant, so we can write a single constant at the very end. We c is any real number. So, our first rule is that integral u plus v dx, u of x dx and v of x dx is the same as integral u dx plus integral v dx, assuming that u and v are functions of x. So the integral of a sum is the sum of two integrals. What happens if I have, for example, integral of 5x cubed dx? Remember that when we differentiated, for example, 10x to the power of 7, this was the same as 10, the derivative with respect to x of x to the power of 7. So the constant of differentiation went in front. Same happened here. Again, because integration is inverse operation to differentiation, I can write this the same as 5 integral x cubed dx. So it's 5 x to the power of 4 over 4 plus c, any real number. So now we've learned that integral x to the power of n dx is the same as x to the power of n plus 1 over n plus 1 plus c. We see any real number and any real number except for 1, minus 1. We also learned that integral u of x dx, u of x plus v of x dx is the same as integral u of x dx plus integral v of x dx. And we learned that integral a u of x dx is the same as a integral u of x dx, where a is a constant, real constant. Before practicing the rules from the previous slide, I just want to make a short comment about this dx. What's the difference between having integral, for example, a x squared dx and integral a x squared dA? If we integrate with respect to x, then x is a variable and a is a constant, assuming, yes, that a does not depend on x. So this is going to be the same as a integral x squared dx, which is a x cubed over 3 plus c. Whereas, if we integrate, with respect to a, I wrote the same integral, with respect to a, then x is a constant, therefore x squared is a constant, and a is a variable. So this is the same as x squared which is a constant here, integral a dA, which is going to be x squared times a squared over 2 plus c. In some of the cases, because a formula that we learned works for non-natural integers, we don't necessarily have polynomials. So what if we have, for example, integral square root of x dx? This requires rewriting square root of x to the power of 1 over 2 and using the formula. Of course, we do not leave it like this, so we need to bring it to the simplest form. X to the power of 3 over 2 is, if you want, x square root of x over 3 over 2, 2x square root of x over 3 plus c. Remember, when we differentiate, we need to work with indices, because that's how our formula works for indices. But then when we write our final answer, if the aim of the exercise is just to differentiate, we can leave it also x to the power of 3 over 2 times 2 over 3. That's perfectly fine. But if we need it further, then it's much easier to work with us in the search form. If, for example, we want to find something about this function, solve an equation using this function, it's much easier to use the search form.